we're going to look at graphing exponential functions. So we've been given two equations, and one equation is a concentration of a pollutant. It's a concentration of a pollutant measured by the population. So P stands for our population in our first equation here. And then in our second equation, this is the formula for population. Population of whether it's bacteria in a lake or people in a city is measured by RT in time. So we want to build one function out of this. So since this is our population, we're going to replace P with the function it is equal to. So we'll highlight in orange here. We're going to replace P with these values here, and then we'll see if expanding or not expanding is important. So when we go to plug this in, our concentration will not have to be a function of time. Our P will essentially be gone from this equation. So our new third equation will be C in terms of time, 1.54, and then we'll replace it with our 12.1 times 2 to the power of t over 52. Okay, and all of this is added to 58.55. Excuse me. So now this is a concentration in with respect to time as time passes, and it's an exponential function. So we want to graph this. What we're going to do is just show kind of what our if we were to transform an exponential function. So say it was, actually we'll use base 2. So we have base 2x, okay? We have an a value, we can multiply that by. We have a k value, we can multiply the x by. We would subtract by, you guys use d, I think? And we would add by a value of c. C will deal with vertical translation, so moving the function up and down. A will deal with stretching a function vertically, up and down, so it would be stretches or compressions or flips. K will deal with horizontal stretches, compressions, and flips. And D would deal with horizontal translation, so moving the function left and right. So, actually, this is set up decently well. What we can do, and there's one other key note for here for an exponential function. It's good to know that we'll write it in without these a, d, c, and k values. A lot of times exponential functions are written like this. They'll write it as an a to some base to the power of k. And when written like this, a is essentially your y-intercept. This is your y-intercept. That's under the assumption that the c value here is 0 at the time, okay? And that our d value is also 0. So the reason this is because if we were to plug into any exponential function, so say we have 3, so we had 4 times 3 to the power of, x. A y-intercept is when x is equal to 0, so we're left with 4 times 3 to the power of 0. This essentially makes a value of 1, right? So 4 times 1, that is your 4 value, and that was originally our a in this case. Now, in ours, that works out almost decently well. We have one little thing. The 12.1, assuming that we didn't have this or this, would have been our a value. But now that we have a 1.54, it probably makes sense to actually distribute the 1.54 times the 12.1, because that will be our a value, and whatever that new a value is will transform or will translate up to 58.55. We'll move it with the c value. So let's rewrite that function down here. C in reference of time is equal to 1.54 multiplied by 12.1 multiplied by 2 to the power of t over 52, and all of that is plus 58.55. Okay, so I rewrote this. I'm going to actually put this in brackets just to show you that this is essentially 3 values being multiplied by each other. Okay, now we really can't multiply into the exponent here because we're not to the same exponent. So the only 2 values we can simplify are these 2 to start at the front. So they'll become our new coefficient. So let's figure out what that actually is. 1.54 times 12.1, 18.634. Okay, So we have a new a value, 18.634. I think that's what it said. Let me double check. Yes. Okay, good. So our new function, c at t. So here's a new a value. We have base 2. We can factor out this 52. Okay? And that would actually be our k value in this case. When we factor it out, the idea is we would just take out 1 over 52, and that's technically being multiplied by a t value. If we were to multiply that, it becomes t over 52. So now we have a k value also, now that we've common factored out this 1 over 52. And finally, our c value is our 58.55. Okay, so that's going to translate the entire function upwards. Okay, so it's important we keep that in mind. Now that we have that, okay, so if we were to do a rough sketch of this function here, okay, just using some of the values we have, we remember we said our y-intercept would essentially, that would be our a. So we would originally have an a value at roughly 18.634, okay, and because it's exponential, it's got exponential growth, it would move up like this. But our c value is now going to shift that function upwards. It's going to shift it up because it's positive 58.55 units. So we are now heading upwards in terms of our y-intercept by adding 58.55. So when we add those values together,
77.184.
Beautiful. What was it?
77.184.
Great. So we now have an exponential function that has been shifted upwards, heading up at that value. And finally, we have a k value of 1 over 52. So if you remember our stretches and compressions, when and usually I memorize them off of our a value. Whenever the absolute value of a is greater than 1, it's a stretch. That's the actually complete opposite of our horizontal. Whenever k is greater than 1, it's a compression. Okay. So in this case, our absolute value of a when it's less than 1 but greater than 0, we get a compression, which means for our k, the absolute value of k, when it's less than 1 or greater than 0, this is a stretch. So we have a horizontal stretch by a factor of 52. So we are pulling our function horizontally 52 units. So it's going to be much, much wider looking. Okay, and we could actually, if we really wanted, we could have taken our original function of, let's say f at x is equal to base 2 the power of x, and we could have used our mapping notation. Do you remember mapping notation?
Mm-hmm.
Yeah? What were the formulas for it, if you remember it?
I do it in a chart form.
You do it in a chart form?
Mm-hmm.
Do you remember it as a formula with our x value being...
And you multiply it by a and you add or minus c.
We would probably add c. And we usually actually add the d value too, depending on what it is. In this case, it's not going to make a difference for us. So we could have taken specific coordinates, for instance, that y-intercept, and we could have plugged it through. Our original y-intercept would have been the value of 1, right? It would have had a coordinate of 0 and 1, so that would have been our x and our y. And if we put it through our mapping notation, we would have had 0 divided by our 52, okay, which is not going to make a difference. And there was no d value, so that's going to change immensely. Essentially, we're going to be back at 0 for that. Our a value is 18.634 times our original y, which was a 1, and then it's going to be added to our 58.55, okay? And again, it pretty much produces the same point. This becomes 0 plus 0, so we're at 0. And as we said before, this became 77.184, so 77.184. So that's our y-intercept again, and it's just a much wider looking graph. So if we were to actually bring up... So if we take a look over here, here's our original function, base 2 to the power of x. And now we've written in our other exponential, and you'll notice the y value has shifted up to 0 and 77.18. So the whole thing has shifted up quite a bit, and it's been horizontally stretched much, much more than our original function, as you can see.